kernel. Yes, now it works. Okay. I'm a software engineer at Red Hat. I work on virtualization. Usually work on the lower levels of the virtualization stack, but as you will see, we'll talk about everything low level, high level. There's room for everyone's tastes in virtualization. I will shortly talk about what made KVM successful, what came out of it, what kind of ecosystem developed around it, and how do you use this ecosystem. And then at the end I have a short overview of what will be the next features perhaps in 2012 in KVM and libvirt and all the other pieces of the open source virtualization stack. So this is a famous message, not as famous as the one from Linus, but kind of. It says the following patch set adds a driver for Intel's hardware virtualization extensions to the x86 architecture. And from this message, we can actually see already three characteristics that made KVM successful. And none of these is an obvious thing. Each of these is a precise ingredient of KVM success. It focuses on future hardware. At the time this was written in 2006, most virtualization was done either by paravirtualization, like Xen, or by binary translation, like VMware. Instead, these are both complicated pieces of technology. Instead, what KVM did was focusing exclusively on hardware-assisted virtualization, which actually, if you can use it, has the best performance and the simplest code in the hypervisor. Of course, the point was that no servers at the time supported virtualizations, or almost. But this was going to change, of course, in the next years. So this was a precise design point, and it allowed Avi and the team to write KVM in less than 2 months. The second part is that he says, each virtual machine is a process on the host, the virtual CPU is a thread in that process, and kill, nice, stop, work as expected. This is another feature of KVM. It reuses the whole Linux kernel infrastructure. Again, this is not obvious, because what happens if you start doing KVM and it works great as a proof of concept, and then the scheduler doesn't scale enough for KVM, or it turns out that perhaps you need different tuning, different tweaking of the parameters for virtual machines, and you just go slow. And the third part is Avi's signature, and a third feature of KVM is that it has a witty maintainer that is also a very nice person to speak with. So, looks like it's very good to have these three things and a good hacker that can write solid code quickly for a proof of concept, but are you sure that you can productize these things? How willing are you to bet on the quick adoption of new hardware with the virtualization extension? And how much are you willing to bet on your ability to integrate with Linux kernel development? And how much are you willing to bet on your ability to create a community around your project when you're just working on the bottom layer, the hypervisor within the kernel? So these three were the main things that, the main three challenges that KVM faced. And apparently, it was very successful in all three of them. Now, a KVM maintainer's life is quite tough, as you can see, because you constantly have to face trade-offs and to find the best way to trade off KVM's functionality as a hypervisor and Linux's functionality as a general purpose operating system. So, do you integrate with the kernel or not? Actually, with the kernel, there's really no choice. The Linux community is the Linux community. You cannot change it because it's big, and it can be a bit unfriendly. Sorry, first mistake, slide 6. It can be a bit unfriendly. And KVM cannot fork the kernel because KVM is not Android. KVM is just a piece of an enterprise Linux distribution, for example. It's not controlling the whole operating system as you have it installed on a cell phone. So what Avi and the team at Kubernetes did was to start with a quick and painless integration of KVM in the kernel, and then getting the features later slowly. This was actually quite successful, and a good way to make it successful is to follow the golden rule of contributing to the Linux kernel, which is to not drop things in one single shot. You just slip it slowly in small increments, and for each step, you must justify to Linux that it's actually a cool thing to have and you're not crazy and caring just about your use case. Every patch that you contribute to Linux must look obviously good at first sight. Not easy, but at least you have an idea of what to do. The other major piece of KVM was the client, the program that actually uses the KVM services from the kernel. And integration with KVM was a much less important task. In this respect, you can actually afford using a fork because QEMU is really used only by KVM, unlike the kernel. In fact, even nowadays on x86, you usually use KVM with the QEMU KVM binary, which is a fork. There are still several features that are only implemented by QEMU KVM and not by upstream QEMU. And to do this sanely, you do basically three things. You work as much as possible with upstream. You don't want to come with a code drop that upstream will reject and that has no way to get integrated. You periodically try to get your stuff upstream, and you merge regularly from what you are forking from. And this is taking quite a while to resolve, but nowadays we have 7,000 lines of code from QEMU KVM that are waiting to be merged into the project that QEMU KVM forked from. 7,000 can be a lot, can be little, depends on your taste. The important thing is that they are all relatively easy things to manage. All the difficult parts, the ones that were causing troublesome merge conflicts and constant pain whenever you were merging from upstream, all those are now merged, and there's only painless things waiting to be merged. So in particular, let's see these crazy features that Linux accepted in the kernel. There are basically some kind of hooks from the general purpose kernel components to KVM. In the scheduler in particular, which lets KVM switch from the guest to the kernel and back to the guest in a very lightweight way. And instead, if you are switching from the guest to another process, you go through the whole heavyweight context switching. There is notifiers in the memory management subsystem. Notifiers, basically, you can call them hooks, if you prefer. And this is what allows, for example, KVM to have overcommitted memory and to swap guest memory to disk. Also in the memory management area, an important feature is merging of pages that are from different guests but have the same contents. Typical example is Windows. Windows always zeros pages that are free in the background. If you free a page, Windows tries to turn it to zeros before giving it back to another process, and this is because it saves time. It would have to zero it anyway. But this also means that all the pages that are free across 20 Windows guests, they all have the same contents and they all can be merged together into a single page. And this is very important when overcommitting memory for Windows guests. Another one, probably the most important, I think, it's transparent huge pages. We used to use pages that are 4 kilobyte in size when memory was 60 megabytes, 32 megabytes, 64 megabytes. Nowadays, memory is at least on the kind of machines that run KVM, at least 2 gigabytes. Sometimes you are more in the range of 64 or 128 gigabytes of memory even. And you're still accessing those memory pages in 4K chunks. Transparent huge pages actually let you access the memory in 2 megabyte chunks. And it's a very good speed up for virtualization, but it's also a very good speed up in general. It can actually speed up spec benchmarks on Java benchmarks by 5 or 10%. And that's not something that you have very often, that a single feature contributes 5 or 10% performance improvement. Also in QEMU, there are some interesting features that were contributed from KVM. Migration of virtual machines, support for multiprocessor guests, support for having stable guest hardware. You don't add a disk and then suddenly all your hardware has changed PCI addresses, and what used to be SDA becomes SDC and so on. This is very important for sanity, but also again for Windows guests, for example. You avoid that you have to reactivate the guest just because you added one disk. And also, since, as we'll see later, QEMU is just the bottom piece of the user space stack, it's also important to have a sane interface from QEMU to the rest of the stack. And this kind of RPC from the virtual machine monitor to the upper stack is one feature that was contributed by KVM developers to QEMU. And of course, the number one feature that was contributed to QEMU is support for KVM itself, because it can easily speed up execution of virtual machines by 5 or 10 times. I mean, QEMU itself is a hypervisor. KVM is just an accelerator. The big part of QEMU is actually reused when running KVM guests. And actually, this is the number one feature of KVM. As I said before, it's simple. It does nothing. It only runs the VM for you. There is no policy decision that is part of KVM's business. KVM doesn't know if you identify virtual machines by a number, by a UUID, or whatever. For KVM, a CPU is a thread and a virtual machine is a process. That's it. KVM does no security checks. KVM does no memory management, no scheduling, tries to do nothing about NUMA machines, for example. All of this is done by the kernel. It's not just a decision that saves development time. It also gives enormous flexibility, and you can use KVM however you want. So, altogether, let's see, these are the ingredients of KVM success. It was built entirely around the components itself. Everybody could tinker with it, download it, play, contribute patches, report bugs, and so on. It didn't just use these open source products as foundations. It also successfully contributed back major new features to both. KVM stimulated the growth of a large and open community around open source virtualization, and it enabled the creation of a large software ecosystem that contributes literally dozens of major products and a lot of people that are just using KVM just to learn things, to do things the open source way, the free software way. And another important thing is that KVM's success has both technical factors, good design choices and good hackers working on it, and social factors, such as actually not being just good hackers, but also being able to stimulate other people to work on your project and work with you on your project. And I think this is a big thing for open source. The technical factors and the social factors are not separate. What you need to do is to create a virtuous cycle where the technical factors and the social factors reinforce each other. So, to sum up, you may think that here is how you use KVM. You just have this QEMU binary and you invoke it, of course. And we have a virtual machine. Unfortunately, there is some fine print. This is how you actually start the virtual machine. So, when you use Zen, you have the Zen hypervisor, you have Zen DOM 0, you have all these components, and you have a rich environment of tools that build upon the hypervisor. Now, KVM gives you all this flexibility, so you can actually just run your virtual machine with QEMU, but it's not really the perfect way to use KVM. So you need something up there. And this something is libvirt. The goal of libvirt, as taken from the website, is to provide a common and stable layer sufficient to securely manage domains on a node and possibly manage them remotely. In practice, this means that libvirt provides an API to manage domains locally and remotely, and actually not just domain, also storage, network, and all components of the virtual machine. It also provides a daemon that handles remote communication, configures the server to run the virtual machine, and also it sits above QEMU and handles the life cycle of the virtual machine, start virtual machine, stop it, migrate it, and so on. It was started around the end of 2006, and it supported KVM and Zen around June, let's say 2007. So what you do is this. You have Zen with its own family of tools, and you have KVM with QEMU, and libvirt can talk to both. And you have tools such as Virch, which is a small command line shell, and Virt Manager, which is a graphic user interface. And Virch and Virt Manager talk to libvirt, libvirt talks to QEMU, and QEMU uses the hypervisor support in the kernel. Actually, libvirt grew nicely, and it doesn't support only KVM and Zen. It supports Hyper-V, it supports CSX. Both of these are proprietary solutions, but you can manage them the same way as Zen or KVM guests. It supports Linux containers, it supports user mode Linux, and a bunch of others. So, with libvirt, you can manage all of these hypervisors, and libvirt can both talk to other open source hypervisors, talk to proprietary hypervisors, or talk to QEMU, which is kind of a different way to manage a virtual machine. This is what libvirt does. It manages the host, which is a big thing to do. You have to start and stop virtual machines, of course, but also manage the virtual networks, manage bridges, manage IP tables to do net of a private network for the virtual machine. You can use more high-end equipment, which is pretty complicated even to explain and to understand. Same for storage. You can just work on a local disk. You can work on an image that is stored on the network via NFS, or you can use high-end fiber channel, SAN, and so on. Another major component of libvirt is that it provides the isolation between the virtual machine and the host. In case something goes wrong, or libvirt tries to make it go not too wrong, not badly wrong. Compromised virtual machines need to be prevented from accessing other VMs, or even worse, escalating to the host and do nasty things on the host's network. You might well have a virtual machine that is facing the public network and the host that is not facing the public network. And you need to avoid that a compromise of a public facing virtual machine reaches the private network and your DMZ. So libvirt provides containment in case the hypervisor security is breached. And this is based mostly on SE Linux and C groups. And it works particularly well on KVM because all that you do with SE Linux and C groups in KVM can be applied to the QEMU process and through the QEMU process to the VM. There are several users of libvirt. Virt Manager was the first graphical user interface that was written for libvirt. It is pretty comprehensive. There is another one that's called Boxes that is being worked by the GNOME guys, and it's more for actually people doing desktop virtualization, like using virtual machines on really just for instead of dual booting, basically. But a major part of libvirt clients is other APIs that libvirt provides. You can access domain information or, in general, libvirt information via SNMP, via AMQP, which is a message queue protocol that you can run and send information for monitoring the host from elsewhere via Matahari. And there's also an open standard to describe guest, resource pools, and so on. libvirt works heavily with XML documents, and this CIM is the open standard that provides an abstraction on guest and resource pools that can actually replace these XML documents. There are also low-level APIs that wrap libvirt using glib and gobject. They provide basically an alternative API that can be more easily then wrapped again in Python, Ruby, and so on, JavaScript, using gobject introspection. And there's also in this family of glib, gobject-based libraries, there is libvirt gconfig, which is an API to abstract the libvirt XML schemas. And other libvirt clients are command line tools. Virt install is basically a command line program to provision virtual machines, and DOS is part of Aeolus. Aeolus is an open source project. It's mostly for managing clouds and managing virtual machines that are running not on your own servers, but rather on a cloud. Actually, as part of Aeolus, there is Oz, and Oz is another virtual machine installer that much more complete than virt install and more powerful. And two other tools that are not based on libvirt but very useful and also talk to QEMU in the same ways are libguestfs and the command line interface, which is called guestfish. And they are useful to inspect virtual machines, gather information from the disks, and so on. So this is how the KVM, a KVM host looks like. It has KVM, QEMU, libvirt with all those providers above. And it has libguestfs that can be used via guestfish, or with Fuse you can just mount your virtual machine images on the host. So the libvirt ones can be used locally and remotely. And this is very important as we go to the next step. Is this really how you use KVM with Virt Manager? Virt Manager can manage, in theory, also the remote part using libvirt, but it doesn't really do that very well. When your challenge is to manage tens of thousands of virtual machines and make each of it accessible from hundreds of or thousands of nodes and hundreds or thousands of thin clients on the other side. Basically, what libvirt does is to provide a host agent. As I said before, it manages the storage, it manages the network, it manages the life cycle of the VM, and it manages security. But actually, when you have a large-scale virtualization, you have many of these host agents, and you need some kind of management engine that takes care of a lot more things. It must take care about creating the VMs and provisioning them, migrating them in case a node has to go down and you need to migrate the virtual machine to another node, bring down the node for maintenance, or when one node is almost empty but not really, you may want to migrate again to another node so that you can save power. On the other way, if a virtual machine suddenly starts having a huge spike of activity, you may want to migrate other virtual machines to other nodes in order to keep the load nicely balanced across the cluster. You have done all these activities about with all these nodes, and you actually want to provide a report of what problems arrived and how they were solved and so on. And also the storage must be managed not only for each single node, but if you are actually running on a SAN, you need also some kind of management across the whole cluster. And also you need something that runs in the guest, also for monitoring purposes, but also for nicer integration with the host, for example, providing single sign-on, and also to respond to management actions. Of course, you cannot expect collaboration from the guest, but you can at least try. For example, you can ask the guest to hibernate instead of doing a non-live migration. There are several solutions for this with kind of different aims. There's OpenStack that is probably the one that you have heard of if you were in the cloud dev room this morning. And actually OpenStack is a relatively new project. There is another project that's called OpenNebula, and I think the talk about OpenNebula is concurrent with this one, so you are missing it. And both OpenNebula and OpenStack are more targeted about providing a cloud and letting your users run virtual machines on your cloud. There's Ganeti, and Guido talked about it before, so it has a very interesting focus on replicated storage that is pretty much unique to it, even though it's coming in both OpenStack and Ovirt. And Ovirt is the last one, and the interesting feature of Ovirt is that it provides a very complete administration interface where you can actually manage thousands of virtual machines on hundreds of nodes and assign storage to each of the virtual machines and so on. Wow, this is ugly. So, as you can see, most of them have roughly the same features. ONE stands for OpenNebula, and Nova stands for OpenStack Compute. Some of them are lacking. For example, Nova, at least now, doesn't have support for live migration, and Ovirt doesn't yet have support for replicated storage, even though it's in the works. OpenNebula doesn't have support for replicated storage out of the box, but actually people are using DRBD very effectively with it. Many of them support other hypervisors than KVM, usually using libvirt, though not necessarily. Ovirt, as far as I know, is the only one to provide a guest agent. And Ovirt also is special in that it provides a specialized distro that is very small and runs on the nodes. Ovirt, I'm going to focus in particular on Ovirt right now. It's an open platform for virtualizing your data center. And it's a large project that comprises a lot of different pieces of the stack. Development of Ovirt started at Cumbranet, which is the startup where KVM was created. Ovirt is the basis of Red Hat Enterprise Virtualization 3. And it's backed not only by Red Hat, but also by those companies on the slide. This is Ovirt. It has all the components that were in the previous slide, the engine, something running on the node, and a guest agent. The engine is the part that you actually use, the part that you actually talk to. You can talk to it with a REST API, you can talk to it via a command line, or also there is an SDK if you want to completely drop the administration portals and write your own, and there are people that are doing it and doing really nice things with it. The node is called VDSM. It uses libvirt. It's written in Python, and it's nice because it's very small. It can run in less than 100 megabytes of installed disk space. And the guest agent takes care of single sign-on and managing the clipboard and passing the clipboard to the thin client, for example. And it supports both Linux and Windows. The most important component, of course, is the engine. And there will be plenty of talks on all the components and especially the engine tomorrow in the dev room. VDSM is the most interesting to me, at least, because it's what actually runs on the host, and it's the part that really, in the end, talks to the code that I write. So VDSM is a libvirt client, though it doesn't use libvirt for everything. It uses libvirt mostly for starting the virtual machine and talking to QEMU. And what VDSM does basically is to provide a high-level API that can be used by the Ovirt engine. And it's VDSM that is asked to migrate virtual machines and so on whenever all those actions for power saving, load balancing, and so on take place. VDSM is able to manage various kinds of storage, and it has some very nice features for team provisioning, even though these are probably the place where the open source virtualization is still lacking compared to proprietary solutions. The things that are in Ovirt are already quite nice. And it provides also the monitoring engine for monitoring both the host and the guests. And of course, since it's actually the part that runs on the same physical host as the guest agent, it talks to it as much as possible and attempts to provide an integrated experience for the user of a remote desktop. So there are still a lot of things to do. There are still a lot of gaps to close, but we are getting there, and we are getting there fast. One interesting feature of the Ovirt engine was that it was written in C#. It used to be written in C#, and it required a Windows machine to run it, and it still requires kind of a virtual machine, a Windows machine to actually administer the virtual machines. We have a new user interface that removes the last piece of Windows dependency. The whole application was partly rewritten, partly converted from C# to Java. And also the new web user interface will be more powerful than the old one, and will have reporting integrated into the user interface. Right now the API is mostly to create virtual machines, not really to use them. So another important part that will come soon is to create a public API, not just a REST API, but also a programming interface for the users of the engine. And also, I was saying before about that still there is no support for distributed storage, and this is going to change with added support for GlusterFS. And there's a lot of work to do not only on the engine, but actually at all levels of the stack. VDSM is going to add support for live snapshot, live storage migration, sharing disks between virtual machines, so that you can have a cluster made of virtual machines. Adding backups, really, storage is an area where there is a lot of work going on at all levels of the stack. Another interesting point is service level agreements is something that can be done very nicely using C groups under Linux, and using these features in VDSM is going to come soon. Ovirt node only supports Fedora right now, actually a custom spin of Fedora. And they are going to add support for additional distributions. I think the first will be OpenSUSE. I don't know if Debian derivatives are coming. libvirt is a major part of the virtualization stack because it's where the integration with the operating system actually happens. And major new features in libvirt space will be fine-grained access control, so that for every tuple of a user working on a given object and doing something to that object, for each such tuple you will be able to say yes, no, and actually get this kind of access control is useful also for to avoid breaches and improve containment. SE Linux, as I said before, right now is mostly a KVM feature, but it can be applied very well at least to LXC. And adding confinement to LXC is very important for sandboxing. A very nice way to run a sandboxed application is to just make it the only application running on a virtual machine. You can do it with KVM virtual machine, or you can do it with LXC. Both of them have advantages and disadvantages. For networking, Open vSwitch is something that was kind of network bridging on steroids that was merged into the Linux kernel, and adding support to libvirt is important because it can add many features and many kinds of isolation and communication mechanisms between virtual machines. And also we are getting network cards that are more and more powerful. Some of them actually have a pool of even 64 Ethernet port on them, and getting this usable in practice, because managing manually 64 virtual network cards is impossible. So improving support for SRIOV is a major part of what is coming to libvirt. And finally, libvirt will, to some extent, take care itself of communicating with the guest agents. Most clients of libvirt are using it especially for virtual machine lifecycle, and asking the guest to suspend or hibernate is important to have a smooth handling of the lifecycle. Going down in the layer, the next layer is QEMU. Again, storage is a major piece of where development is going on. I personally am working on a virtualized SCSI controller. There are many advantages of having a virtualized SCSI controller device rather than just a disk. The main one is that there are, well, very simplifying, there are smaller differences between what hardware a virtual machine sees and what hardware the same machine running on bare metal sees. They will both see SCSI disks, and the smaller the differences, the easier the management. Also supporting team provisioning, live storage migration, and everything in the previous slides has to be done first of all in QEMU, and then can be done in Libvirt VDSM and so on. Another interesting thing in QEMU is that the object model of devices, disks, networks interface, and so on is going to be unified, and this will provide a simpler management interface, a simpler RPC, and get improvements for hot plugs. And further down, KVM is also going to have better integration with OpenVSwitch. Part of the networking is done in the kernel, because you can actually have very nice performance improvements by cutting out user space on network input-output from the form and to the guests. So OpenVSwitch will provide again functionality, but there's also work on zero copy and performance improvements. And one nice feature that might be more interesting to the hacker audience as opposed to the sysadmin audience is virtualized performance counters that actually lets you run profiling of something running in a virtual machine. Here are a few links to projects that I mentioned, and some others that actually I didn't mention, such as Eolus, or mentioned very briefly. And now if you have any questions, I will be glad to answer. Yeah.
Hello, I'm Andrzej. I'm from Every City. We are big supporters of Solaris and Illumos projects, and we are looking to using KVM on top of Illumos kernel. And I have just a quick question. Who would be the best person to speak to about improving KVM support on top of Illumos?
I guess. So the question is, he's interested basically in using KVM on top of Solaris. The port was done by the guys at Joyent. They presented it to the last KVM forum in August 2011. And he asked who to contact to get information on development and support and improvement. Is this right?
Well, I mean, Joyent guys, they are interested on KVM on top of Intel hardware. But I was wondering if there was someone within KVM on top of Linux community who would be helpful and supportive if we had any problems with KVM on top of Illumos.
Okay, so support can be given by anyone. Most of the problems will probably be in the whole stack, not just in the kernel port. And for that, probably every development can answer it. If it really resides in the kernel, only the developers can provide support.
Yeah, I mean low-level support, kind of.
Low-level support, only the guys who did it.
So, for example, Joyent guys, they are not interested in AMD support. And I know that KVM on top of Linux works just fine on AMD.
Patches are welcome. I mean, you write a message to a mailing list. If somebody says they are interested, you can work with them. Otherwise, you have to do the work yourself.
Okay, thank you.
Sorry.